So we are starting section 5.4, guys. What we have before us is a normal distribution. You agree with me, guys? It is a normal distribution. It looks like bell-shaped. The mean here is 25, and the median, well, the mean and the median are the same, as you know, if it is a bell-shaped distribution, and the standard deviation is 5. I could change this one to make it any number I want, but I want to start with the mean of 25 and standard deviation of 5. We're going to collect samples of size 5. So each sample has 5 values, guys. And we're going to ask this applet for each sample to find, the sample mean and then graph it for us. So I'm going to begin just one time and just see that in action, guys, what's happening. Look, 5 values are being picked up, and then the mean is being calculated and put right at the bottom. If I pick another one, guys, watch. And then let's pick another one just to show you. And then the applet computes the mean. Okay, now we're going to do it 1,000 times. So what's going to happen, and it's all happening, guys, before you blink your eyes. I'm going to pick 1,000 samples of size 5. The applet is going to find 1,000 means and put them in a histogram format here. Watch. It's done. Let's do another 1,000. Another 1,000. Another 1,000. Another 1,000. Okay. Another 1,000. Another 1,000. All right. How many samples do I have here? Can you guys see it right here? It's 11,000 samples. You can ignore the 3 that I did to begin with. I have 11,000 samples. So we collected 11,000 samples. We computed the mean of each of the samples and we plotted them, and we have this kind of histogram. So this is a bell-shaped curve for the sample means. This is a bell-shaped curve for the actual values in the population. So the black one is the population values. The green one is the sample, the means from the samples, from the 11,000 samples. So I have 11,000 values here. I would like you guys to make some observations. If I ask you to compare the two curves, what would you say? Look at the black one and look at the green one. What do you observe?
The population is more spread.
Where? In the black one? Good. That's very good observation. So that means the standard deviation of the original population is higher than the standard deviation of the sample means, of the means from the sample. That's an excellent observation. And watch, guys. What is the standard deviation of the original population? Can you see what I'm highlighting? It's 5. Can you read the standard deviation of the sample means, guys? What is it here? 2.24. So it's less. That's one observation. Give me a second and third observation. There are 2 more observations you should be able to make. Look here, guys. Just look at those values, top and bottom. What do you notice? Something very, very important. What is it?
The mean and the median are different.
Okay.
Just by a little bit.
The mean. What's the mean? What is the mean for the original population? 25. What is the mean of the sample means? I want you to round it to the whole number. If you round it to the whole number, it will be the same. Actually, the means are the same. They should be exactly the same. Okay, they have the same mean, which is good news. When you work with samples, actually, you're still getting the means of the original population. Okay, so the first observation, they have the same means. The second observation, you said one has a smaller standard deviation. I agree, that is correct. What do you think of the shape of the green curve? Do you guys agree it is a bell-shaped as well? It is a bell-shaped curve, so it's a normal curve. So the distribution of the means, the sample means, is also bell-shaped. Now, I would like you guys to take the standard deviation of 5 and divide it on your calculator by square root of 5 and see what you get. Now you ask me why square root of 5, because we put a sample size of 5. So try, guys, to do 5 divided by square root of 5. And just tell me what answer would you get on the calculator.
2.2360.
All right, let me just do that myself. 2.2360. Do you notice that, guys? It's very close to this one, which is 2.24. So if you take 5 and divide it by square root of 5, you will get the one that we have here from the experiment. So we don't need even to perform the experiment to figure this out. You'll get it approximately, not exactly, but approximately. Okay, let's do the experiment one more time, guys. And now I'm going to change the sample size. So I'm going to refresh, reset. I'm going to change the sample size, guys, to 25. And let me show you what's, and if you want me to change the mean, I can change the mean. Let's make it, for example, 60. Oh, I have to go back and change it. Let's leave it 25. So 25 standard deviation is 5, and we're selecting samples of size 25. So let me show you just one sample, show you the applet in action. So what the applet did, it took one sample, 25 items, and gave you the mean of the sample. Well, let's do it in thousands now. I'm going to do 10,000 samples. Oh, we went more. Okay, let's do, okay, 15,000 samples. That's good. I got 15,000 samples. Okay, observe, guys. The mean of the original population is 25. The mean of the sample means is also 25. I mean, you can say 0.0014, but that can be ignored. It's so small that you don't even need to take this into account. Now, what I like you to do, guys, I like you to take the standard deviation of 5 and divide it by the square root of 25. What is the square root of 25, guys? It's 5. What's 5 divided by 5? 1. Well, look at the bottom. If you round this to 2 decimal places, you will get 1. You notice it's a lot smaller standard deviation than this one, and you can see the curve is very narrow here just simply because it has a smaller standard deviation. So the advantage of working with samples, guys, you will work with the same mean as the population mean, but you will work with a smaller standard deviation, which is good news. The smaller the standard deviation, the more consistent the data is with the mean. That's why it is preferred to work with samples rather than working with individuals from the population. So that's one observation that I like to make. Now, I'm gonna just change, refresh this one. And I'm gonna change this one and make it skewed distribution. Okay, let's see. All right. You can see, guys, this is a skewed distribution. It's not a bell-shaped distribution anymore. So I'm going to pick samples of size 36 here. And I'm going to do this 1,000 times. And look, the mean, remember the mean is 22.18, and the standard deviation is 8.25. Just keep that in mind. Let's do 1,000 times. Remember, your original population is not bell-shaped. Let's do another 1,000. Okay, that's enough. I did how many? 10,000 samples. Okay. Can you give me some observation, guys? What do you know? So what is the mean of the original population? 22.18. What is the mean of the new population? 22.18. It's the same mean. Even if the original population is not bell-shaped, when you pick samples, you end up with a population that has the same mean. But I'd like you guys to take this standard deviation, 8.2588, the original one, and divide it by the square root of 36. Can someone do that for us?
1.3.
Square root of 36 is 6. So what do you get? Let me see. 8.2588.
1.3764.
At 1.3764. What do you guys think here? Beautiful match. 1.37 if you round to 2 decimal places. Same thing is happening, but the original shape is not bell-shaped, but look at the new shape of the sample means. Do you guys notice that it is still a bell-shaped when you do sample means? It's always a bell-shaped. Even if the original population is not, when you pick enough samples of a large size, 36, it turns out, just to be bell-shaped as well. Okay.
Does it change? Because I noticed when you were adding the 1,000 times, it was starting to become symmetric.
This one, yes. Yeah, it will eventually become symmetric. That's the conclusion I want to make. When you do work with samples, the population of the samples will become symmetric, definitely. Let's change this one a little bit now. Just make it any population. Look at this population, guys. And I'm gonna pick samples of size, let's say 100. Large sample size. And I wanted to observe, guys, what's going on. So remember, this original population is not normal. Let me do 10,000 samples. Here's 10,000. Okay, guys, notice the mean of the original population is 23.73. The mean of this population is 23.73 as well. And you notice how big the standard deviation in the original population is. It's 9.48. Look at the standard deviation and then population in the distribution of the means. It's 0.94. Here's what I like you to do, guys. I like you to take 9.48 and divide it by square root of 100. So I think now you know what the formula is going to be to find the standard deviation of the sample means. So take 9.48 and divide it by square root of 100, which is 10. So you guys agree with me, it should be 0.948. And look here. It's almost a perfect match. And I've done all this work. I showed you the results, guys, without even doing anything by hand. It's a random applet that runs, just the work in the background. And what we're gonna do, guys, is just whatever you observed right here, I'm just gonna write them down on the guided notebook and show you how we can use those results, to answer questions pertaining to samples, not individuals. Okay. So in red, it says, watch the simulation demonstrated in class carefully and then write your observation. So we did watch the simulation, guys, and we're gonna write the observation together. The central limit theorem. We had two graphs, guys. I showed you two graphs. One is the original population, which is we do not do it by X. It has a mean and it has a standard deviation sigma. And the other graph that I showed you was the sample means. And we denote the sample means, guys, with X bar. So to refer to the sample means, which is X bar. Okay, did you guys agree with me that what we notice here, that the two means were the same? So the mean of X bar was the same as the original mean. They have the same mean. But you do agree with me that this curve was a little bit narrower than the other curve. So what I was asking you to do here to find the new standard deviation, I asked you to take the sigma and divide it by square root of n. And this is the new standard deviation, guys, of the sample. It's called sigma of X bar. So these are the two observations that we're gonna write down. Use mean for original population mean and mu of X bar for the sample means. Use sigma for original population mean and use sigma of X bar for the mean of the sample mean. And that's what I'm using right here. The mean of the sample means, guys, mu of x bar is equal to mu. They are the same. You saw that in the applet. The mean doesn't change. The standard deviation of the sample means is equal to the population standard deviation divided by, can someone tell me how do you say that in words? Sigma divided by, how would you say this? Square root of the sample size. That's what we did, guys, and we noticed that our answer matched, with what the applet showed us. And also we observed, guys, when the original population is bell-shaped, then the distribution of the sample means is also bell-shaped, which is normally distributed. Not perfectly, approximately, but it is normally distributed. Remember, the word normal, guys, is bell-shaped, regardless of the sample size. Now, I also showed you in the applet that it is possible for the population not to be bell-shaped. It could be skewed. I did show you an example, but I chose a large sample size. I picked 36 and 100. Okay, let me write a note about this. When the original population is not normally distributed, then the distribution of the sample means will still be bell-shaped, normally distributed. Provided that we use a large sample size. I used 36, I used 100. The cutoff, guys, is you have to use a sample size more than 30, provided the sample size is more than 30. It's beyond the scope of the course to discuss this number, but in statistics, a large sample size means it has 30 or more values. That is what a large sample size. And this is what we did, guys. Let me show you what we did. I did a population like this. I chose a sample size more than 30, and we ended up with something like that. The sample means was bell-shaped as well. Then we did a normal population. I started with a sample size of 5, if you remember, small sample size, and it turned out to be a bell-shaped distribution as well, regardless of the sample size. So when your original population is bell-shaped, it doesn't matter what the sample size is. It does not matter. When your population is not bell-shaped, it's a skewed distribution, then if you want to get the same results of the central limit theorem, you must use a sample size that is 30 or more. So more than 30, probably here I should have said more than 30 or equal to 30. 30 is okay. So we write it like this. And this is the central, what we call the central limit theorem. What matters to you guys, how can I apply this theorem? So I'm just going to show you now how to apply this theorem. So in summary, guys, if you want to memorize anything about this theorem, is this. When you work with X bar, with samples, working with samples, the mean of X bar is the same as the mean of the original population, and sigma of X bar, the standard deviation, is the standard deviation of the original population divided by square root of n. This is the summary of the central limit theorem. They call it CLT, central limit theorem. Okay, let's see some few questions and how to do.
Could you show
Yes,
that one more time just so I could copy it down?
sure. That's it. These are the two.
And what does CLT stand for?
Central limit theorem. That's the title of this section 5.4, central limit theorem. Google it, guys, YouTube it. You're gonna get millions of hits on that one. So if you like to learn more, just go to YouTube, watch some videos on the central limit theorem. But the applet, I think it's a very good way to explain it. So let's see exercise 11 and 12, just to begin with. Cellular phone bills for residents of the city have a mean of $63 and standard deviation of 11. So mean is 63 and standard deviation of 11. Random sample of 100 cellular phone bills are drawn from this population. Can you guys tell me what letter do I use for N? Well, I just said it. It's N. That's a sample size.
X bar.
No, that's N. Random samples of 100 cellular phones. So that's the sample size. So you see, we're not picking one phone here. We're picking 100 of them. So now you're working with samples that you are in the central limit theorem mode. Are drawn from this population and the mean of each sample is determined. So X bar is determined for each sample. What is the mean and the standard error of the mean of the sampling distribution? Okay, what he wants, guys, he wants the mean of X bar. And the standard error of the mean, it's sigma of X bar. They call it also a standard error of the mean. And you already learned in the theorem that mean of X bar, guys, will be the mean, which is exactly the same as the original mean. And what is the original mean, guys? It's $63. What is sigma of X bar, which has another name, guys? It has a standard error of the mean, which is sigma divided by square root of n. What is the sigma? It's $11 and divided by square root of 100. And what would be 11 divided by square root of 100, guys? It's $1.1. In other words, guys, when you work with samples, there is less variation than working with the original population. If you work with the original population, your standard deviation is 11. If you work with samples, guys, your standard deviation is only $1. That's why it is preferred to work with samples than working with the original population. Now he says, sketch the distribution of the sample means. If you want to sketch it, guys, you will just sketch it like this. You put 100 here. And can a student tell me what would be the three numbers that goes to the left and the three numbers that goes to the right? And we're working with X bar here, remember. What would be this number, guys? Any guesses?
1.10.
80.
So we have to add a standard deviation. So what would that be? Don't we add one standard deviation, two standard deviation, three standard deviations? So what would be the next one?
111.
But remember, we're not working with X, we're working with X bar. It is 111 if you're sketching X, but we're not sketching X, we're sketching X bar. So what would be the standard deviation here? 110, guys. So 100 plus $1.10 will be 101.10.
So standard error of the mean
Is the standard deviation, exactly.
Okay.
It's a different name. That's why I put it there. So if you see it, guys, you know. And if you want to know what this number, guys, here, you subtract $1.10. It will be 98.90 and so on and so forth. That could be a question, you know, just on the test. I'll give you three graphs and I'll tell you which one is the graph of the sample means. Remember, guys, and one of the graphs that I will put, it will be 111 here. I'll add 11. You're not adding 11 when you work with X bars. You are adding 11 divided by square root of 100. So you're adding only $1.10 as your standard deviation. The lesser the variation, guys, the better. Exercise 12, same question, I think, just like 11. The training heart rate for all 20-year-old athletes are normally distributed with a mean of 135 beats per minute, standard deviation of 18. So that's the original mean, and that's the original standard deviation. Random samples of size 4 are drawn. So N is 4. and the mean of each sample is determined. Find the mean and the standard error of the mean of the sampling distribution. Okay, same thing, guys. Mean of X bar is going to be the same as the mean, which is what? 135. And sigma of X bar, it's going to be sigma divided by square root of n, which is 4 divided by square root of 4, which is 2. And he wants you to sketch it. Look how I would sketch it right here. Just put X bar here, guys, so you don't forget that it's not about X, it's about X bar.
Want it be 18 divided by 2?
So
Because
135.
18 is our standard deviation, not 4.
Oh, you're right. Absolutely correct. Thank you. Okay, so can you guys help me out here, please? Now you should know. 135, what goes next? Plus what? Decide, plus 9 or plus 18? 9. We're working with X bar now, guys. Still large, but better than 18. So 144. Do you guys know why this turned out to be still a large standard deviation, whereas here the standard deviation of the sample mean became very, very small? Do you know what affected that? You should know.
The larger n.
Exactly. When you have a larger sample size, it's a good thing in statistics. You will get less variation. If I want to survey you guys, if I pick 2 students and survey 2 students, I get results. But if I want to get more accurate results, I'll pick 15 students and survey them. I'm going to have a better consistency this way. The larger the sample size, the better. So that's why you got a 9 here, but here you got a 1.1. And then if I add 1, guys, will be 9, 153, and then will be 162. And here, subtract a 9, will be 126, 117, 108. And that should be your graph. And look, I'll label that as X bar. Okay. We'll end our discussion with a real.
I have a question really quick.
Go ahead.
For 11, we used n to graph our sample distribution. And then for 12, we used the mean.
Oh, no, we didn't use n. No, we used, oh, I made a mistake. I was thinking it's 63. You're absolutely correct. Thank you. Somebody is paying good attention here. That's wrong. It should be 63. I was wondering, why did I put that?
So we're using the mean to graph both.
Yeah, definitely.
Population and sample.
Thank you. Thanks for noticing that. Let me just put it somewhere here. Oh, sorry about that. We never use n. I just was thinking it was the mean for a second. I guess I need a break after this. Okay, so it is 63. You're absolutely correct. Thanks for noticing. X bar, and then 1.1, guys. So I have a room actually to do it. So it will be 64.1, 65.2, and then here, guys, subtract 1.1, it will be 61.9, and subtract 1.1, it will be 60.8, and so on and so forth. That will do it. Right. This is for 11. Yeah, you put the mean and add a standard deviation. Last question, guys. Now you will see how to find the probabilities using samples. That will be the last one. Furnace repair bills are normally distributed with a mean of $266 and a standard deviation of $15. If 36 of these repair bills are randomly selected, you see now we have a sample size of 36, so n is 36, guys. what is the probability that they have a mean cost between $266 and $268? So look, this is the question, guys. You pick 36 bills at random. What is the probability that the average amount on the bill is between $266 and $268? So let's, it's going to be a probability. It's going to be a normal CDF. So we begin like this, guys. We put 266 less than 268. And what variable will go here, guys? What's the variable that we usually use here? What variable did we use in the previous sections, 5.1 and 5.2? Show you here. X. It's all about X, but what does he say here? What is the probability that they have a mean cost? A mean cost, guys, it's an average. What's the symbol of average? What do we use for the sample mean notation? Not X. We use what? X with what?
X bar.
X bar. This is the difference between the previous section and this section. This is about the mean. This section is about the mean. The other section is about individuals, just X. So it's going to be normal CDF. Help me out, guys. 266. Then what? Lower bound, upper bound, 268. Mean. Can someone tell me what to put in here?
Is it the 266?
266, yeah, that's the mean. Okay. Last one. Can someone help me here? What do I put there?
15. 15.
Let me see what I put above this.
You're gonna have to use the equation.
Exactly. We have to use the standard deviation from the samples. That's the only difference between what you learn, guys, and what you're doing now. When you work with the samples, it's not 15, it's 15 divided by square root of n. Otherwise, guys, ask yourself, I didn't use this one. In math, we won't give you information that you don't use in a problem. You have to use it. So now if I remove this and put 15 over square root of 36, and that's going to work. Let me show you. Input second, distribute. Nothing new, guys. It's still the normal CDF. 266, 268, 266 for the mean. And here you put 15 divided by square root of 36. You can put 6 if you want, because square root of 36 is that. If you put 15, it's going to give you the wrong answer. There you go, 0.2881. Okay. All right, I'm gonna stop here.